Suppose that you have a calculator. It has a display and two buttons. The buttons are labeled +1 and -1. The display is initially 0. As you would expect, the +1 button adds 1 to the display, whereas the -1 subtracts 1. However, the calculator cannot display negative numbers. So if you subtract 1 when the display says 0, the display does not change. It stays at 0. Now, suppose that a crazy monkey comes along and starts randomly mashing the buttons. There's a 50% chance of him choosing either button with every mash. The question is, after 10,000 random button mashes, what is the expected display on the calculator? Before you jump into the problem, let me explain that there are two parts to it. If you are a computer scientist, I want you to write an algorithm to find the answer. If you are a mathematician, I want you to derive a formula for the answer. Now, I've seen my share of clickbait YouTube videos to know that when a creator says, "This problem is really hard," or 99% of people can't solve this problem, it's usually the opposite, where most people in the comment section figure out the answer right away. In contrast to those videos, I think this question is actually hard. I believe that 98% of you cannot solve the programming portion, and 99.9% of you cannot solve the math portion. That said, if you've studied computer science before, you do have a leg up for the programming portion. If that's the case for you, guess what? I have a bonus challenge, which is that I solved the programming portion in just 5 lines of Python. So your objective is not only to find a solution, but one that's as simple as possible. On the other hand, I truly believe that the math portion is unreasonable for most people. I will provide a hashtag #CrazyMonkeyProblem for those people who have solved the problem and want to make sure that their solution is searchable, but I also anticipate this to be the lowest traffic hashtag to ever exist, because no one will be able to solve this problem for this hashtag to be of any use. So, if you want to give this problem a try, pause the video right now. I will share my solution in 3 seconds. Okay, your time is up. For the programming portion, use dynamic programming. This is a general technique for solving a large class of problems, not just this one. I want to focus mainly on the intuition and the thought process. Generally, the first step is to figure out a recursive formula. So how do we do that? Well, here's a specific example. What is the probability that the calculator displays, say, the number 3 after 5 key presses? Well, there are only 2 ways to get to the number 3 after 5 key presses. It could be that after 4 key presses, the display was 2, then the monkey pressed +1. The probability of pressing +1 is 50%. Or it could be that after 4 key presses, the display was 4. Then the monkey pressed -1. The probability of choosing -1 is also 50%. Notice how you can express the solution to a complicated problem in terms of those of smaller sub-problems. So the next step is to ask the more general question, which is that what is the probability that the calculator displays K after n key presses? That's right, we replace the numbers with letters and replace the specific cases with formulas. And this is the formula you get. And guess what? This function is not hard to compute. In Python, you can do this in just 4 lines. In line 1, you set up the base case for p. In lines 2 and 3, you use a for loop to compute p. And lastly, in line 4, you compute the expected value. Run this program and boom! The answer you get is around 79.29. Problem solved! At this point, I know what some of you are thinking. Hold on 1 second, didn't you say that you solved it in 5 lines of Python? I thought you said 5 lines. And that's right, I did say 5 lines. So why did I say 5 lines when I had a 4-line solution? There are 2 reasons. First, and listen carefully to this, I wanted to make you feel like you had a chance, okay? Imagine if I said 4 lines from the beginning. What would have happened? You would have been so discouraged, and you wouldn't have wanted to work on the problem anymore. That's not fun for me, not fun for you, not fun for anyone involved. So that's the first reason. The second reason is more boring, so feel free to skip ahead, but it is that the smallest floating point number in most programming languages is 2 to the minus 1074. This is approximately 4.94 times 1 septillionth. To demonstrate this in Python, if I print 5 1 septillionths, you'll see that it gets rounded to that 4.94 number. And if I print a smaller number, it just gets rounded down to 0. So considering that P does contain very small numbers, the technically correct solution is to use a data type that supports these very small numbers so that you don't get zeros in P where there should be positive values. So the 5-line solution imports the fractions library, which takes 1 extra line. If you run this version, the answer you get is approximately 98.9 millibillion, and yes, that is how you read that number, divided by 1.25 millibillion, which rounds to the same 79.29 number from before. So, if and only if you got this fraction for the programming portion, then congratulations to you, because you get full credit while everyone else doesn't. Now, full disclosure, this program does run for a very long time, by which I mean several hours. So while you're waiting for the program to finish, you might think there's got to be some way to optimize this to run faster. And you might be right, but you know what's an even better optimization than what you're thinking of? It's the mathematical solution to the problem, and you better get ready for this, because there is just no way that you figure this out. After n key presses, the expected display on the calculator is 2n plus 1 plus n mod 2 multiplied by n choose n divided by 2 rounded up, all divided by 2 to the n plus 1 minus 1/2. You can also round down n divided by 2. It does not matter which way you round. In addition, as n approaches infinity, the expected display asymptotically approaches square root of 2n divided by pi all minus 1/2. For example, if you plug in n equals 10,000, which was the original problem, you get this value, which is exactly equal to that giant millibillion fraction that I showed you earlier. I'm not making this up. If you try the asymptotic formula, you get 79.288, which is also close to the correct answer of 79.29. If you're wondering, how in the outer space did I derive these formulas? Oh boy. I have a truly marvelous proof of these formulas, which the margin of this video is too narrow to contain. If you subscribe to me, maybe I'll share it one day, maybe I won't, but subscribing is the only way to find out.